All right, let's look at exercise 6. This is section 2.4. So we're given a function that describes the position or the height of an object as a function of time. And we're being asked about instantaneous velocity. So given a position function, we want to describe the instantaneous velocity. That is going to come from finding the first derivative of that position function. So we'll go ahead and do that. First term in this derivative is a constant 3. The derivative of any constant is 0. So the derivative is going to come exclusively from this 2 cosine t over 1.2 to the t. So that we're going to need the quotient rule for. So let's go ahead and start setting that up. So the numerator is going to look like this. 2 cosine t. I want the derivative of that multiplied by 1.2 to the t. These primes aren't very clear. Let's actually do this. d dt of 2 cosine t times 1.2 to the t minus 2 cosine t times the derivative of 1.2 to the t all over the denominator squared. So 1.2 to the t squared. Okay, so let's start dealing with some of these. What's the derivative of 2 cosine t? That is negative 2 sine t times 1.2 to the t minus 2 cosine t times the derivative of 1.2t, which is going to be what? 1.2t times the natural log of 1.2 all over. For now, I'm just going to leave it like this. 1.2t, it's 1.2 to the t squared. So this is the derivative for any value of t. So now let's evaluate it at 2. So those would give me negative 2 times the sine of 2 times 1.2 squared. Actually, I changed my mind because it's going to save me on some calculator work in a little bit. I'm going to do some simplifying of this derivative. So one thing I notice is that 1.2t, 1.2 to the t, is common to both terms in the numerator. So I'm going to factor it out. 1.2 to the t, and I want to, while I'm doing this, I'll say that this is optional. I'm basically doing some algebra now for a couple of reasons. One is to give myself a little bit of an easier calculation that I know I'm going to have to do very shortly. But also, I also know I'm going to have to find the second derivative. So that's going to make this a little bit simpler as well. So I factor out this 1.2 to the t. I have negative 2 sine t minus 2 cosine t times the natural log of 1.2 all over 1.2 to the t squared. So I'm going to cancel this 1.2 to the t with, one of the two powers down here. So my first derivative now, I think, is as simple as I'm going to get it. Negative 2 sine of t minus 2 cosine of t times natural log of 1.2 all over 1.2 to the t. Okay, so now that I have what I think is a pretty simplified derivative, I'm going to evaluate it at x equals 2. So negative 2 sine of 2 minus 2 cosine of 2 times the natural log of 1.2 over 1.2 squared. So that's approximately equal to what? Give me a second here. So negative 2 cosine of 2 times natural log of 1.2, I'm getting approximately 0.1517. And then negative 2 sine of 2, I'm getting negative 1.8186 all over 1.2 squared, which is 1.44. All right, so final result here, I'm going to say negative 1.16. So that's the numerical answer. What units make sense here? So our height is measured in feet and our time is measured in seconds. So our rate that we found here will be a decrease. So negative 1.16 feet per second. Moving on to part B. Now we're being asked about the object's acceleration. So how do I get acceleration? Well, if I am dealing with a position function, which I am here, a height is a vertical position, I want to find h double prime. So in order to find h double prime, I need to know what the first derivative is. Luckily, we just found it and simplified it quite a bit. So negative 2 sine t minus 2 cosine t times the natural log of 1.2 all over 1.2 to the t. So here's our first derivative. I need a second derivative. So what's h double prime of t? Basically, we're going to run through the quotient rule again. So in this case, our derivative, let's take a step back. Let's define these two functions as this. Let's call this p of t and q of t. So our h double prime of t is going to be equal to p prime of t times q of t minus p of t times q prime of t all over q of t squared. So what is the derivative of our function in the numerator? So negative 2 sine of t, that derivative is negative 2 cosine of t. What's the derivative of negative 2 cosine of t? That'll be, actually, I need to open this parentheses back up. Plus 2 sine of t times the natural log of 1.2. So that's p prime of t. That multiplied by 1.2 of t to the t minus p of t. I'm going to just leave that as p of t times q prime of t. So what is q prime of t? That is, maybe I should, let's do this. Let's rewrite this. I'm already going to take one shortcut here. I don't want to take another. So negative 2 cosine of t plus 2 sine of t times natural log of 1.2 times 1.2 to the t. So that right there is p prime of t, 1.2 to the t, that's q of t, minus p of t. So that's the numerator left unaltered. So negative 2 sine t minus 2 cosine t times the natural log of 1.2 times the derivative of q. So what's the derivative of q? That'll be 1.2 to the t times the natural log of 1.2. And then all of this over 1.2 to the t squared. I'm actually going to leave part B here. To spare you all watching me approximate this nasty expression at t equals 2. But this right here will give us an acceleration in feet per second squared whenever you finish that calculation. Actually, I guess I do need to know what this is doing at. So let's do this. I've shown you kind of how to by hand manipulate this function. So let's jump to Desmos and talk about what this function is doing. So f of x equals was it 3 plus 3 plus 2 cosine t over 1.2 to the x. Okay. So one nice thing you can do with Desmos is since I've defined the function, I can talk about the derivative. So derivative we said was, this is identical to what we had before. Negative 1.15, or I think I said 1.16 feet per second. So what is f double prime of 2? So that's positive 1.019, and we said that would be measured in feet per second squared. So part C here is asking, oh, that's the next thing we're going to talk about. So C, describe in everyday language the behavior of the object at that instant. So based on these two derivatives, I think I can say, let's just keep it in a qualitative sense. 2 seconds after I, started measuring the height of this object, I can say that its height was decreasing. So at this instant, its height is decreasing. So it's going downward. But what does the second derivative tell us? It's going. The second derivative tells us that its instantaneous rate of change is increasing. So at this instant, the object is going downward, but it is going downward more slowly. Basically, its acceleration is upward. So that means its velocity downward is going to be, or its speed downward is going to be decreasing. A lot of ways to kind of capture that. I just gave you a couple.